Welcome to our very short lesson in physics. Today's subject are levers. Archimedes said, "Give me a long lever and a fulcrum, and I will move Earth." Well, so I have here fulcrum. Fulcrum should be like moon, should be big, and the lever should be also big, should be of the distance between Earth and moon, which is 400,000 kilometers, which is much. It's not very practical. Well, but the idea is not bad, because in order to have a big force, we can use much smaller force of our arm, but use a long lever. Exactly the difference, the ratio between forces is like the ratio between the length of the two parts of the lever. 10 times bigger force, 10 times longer lever. At the end, to move the lever, we must do 10 times bigger path. If we go to the discussion about the work which we need to do, it's exactly the same. But the idea is not bad, and we have a lot of applications of levers. Well, just in this seesaw, it's easy to understand because the mass, the weight of the two players are equal. So the distances between them from the point of rotation is the same. But in the case of this surfer, this part, the length of this branch is much bigger than this one because the ball is much heavier than the surfer. They are in equilibrium because the product of the length and the weight is the same. I have a lot of things to play with. This is a shark that can close the jaws and at a distance, because I have a lever here which changes the direction, which changes the forces, and then a rope hidden here, and then another lever here making the movement. The same exactly with this dolphin. When I move the jaws, the bear will make its acrobation. The bear, again, we have a lever hidden here. I will squeeze on this part using short lever, and this is much bigger, but then the movement of the upper part is bigger. Let's do it. Well, it makes its acrobation, and this acrobat is even better to see. This distance is shorter than this one, so the movement of the upper part will be bigger. Let's hope that will make its scenario. Well, it works. Then we can clasp automatically. I squeeze here, I move the levers here in an exact way, and we can clasp. It's very useful during matches. And this acrobat, again, lever is hidden. These are small wires that I push, but they change the movement, which is short in this direction, to a big bending into other direction. Well, you would say we play. No. The dictionary, English dictionary, says that lever is a strong tool. So I have a number of tools here, starting from scissors. I want to cut a thick piece of paper, so I will use the scissors close to the point of rotation in a way that this distance is much bigger than this one, but it's cutting quite tough paper. Then these scissors for gardeners, a key to close nuts, closing nuts with a strong force, but using pretty medium force of my hand. Again, the distance is in correct ratio to the forces used. Even a screwdriver, we use a strong force on a small radius using much weaker my hand action. Well, with these pliers, I would even cut a nail Well, I put a nail here, I squeeze, nothing happens. I made an error because I should put the nail as close as possible to the point of rotation to have the biggest difference, biggest ratio between these two distances. Now I can cut this nail. In different gears, the principle is exactly the same. The number of teeth here in the gear corresponds to the force that I need to use. I can use small force to move the big gear and to exercise much bigger force on this side, but then I need to rotate much more on the small wheel. All old clocks are full of gears like this, making transmission of a fast motion of small gear into a very slow motion of the arrows. So physics and techniques is full of levers, and I wish you a lot of fun with acrobats, with pupils and toys from South Tyrol, from Austria, or toys from Italy. This is famous Pinocchio. Have a lot of fun with levers. Thank you very much.